Hi there, Mr. Sutton here, bringing you the Algebra 2 10-7 lesson on using trigonometric identities. This one is going to be a two-parter if you're doing the CP version of the course, and for the honors we will have three parts. In the two-parter part of this, we're going to be simplifying trigonometric functions using identities, and for that third additional part for the honors group, we're going to be verifying these trig identities. If we're doing a lesson on identities, we should probably start that lesson by defining the word identity. An identity is just an equation that's true for all values. And the big thing about identities that we'll be seeing in this lesson is that if you have one of these equations, you can substitute one side of the equation for the other, and this can be very helpful for simplifying expressions. So there's a lot of identities that we're going to be going through here, and that's part of the work we're going to be doing. We're also going to go through some strategies for using those identities. So to start with, let's take a look at some identities you probably already know. So here are four ratio or reciprocal type identities. We've got tan of theta, cosecant, secant, and cotan. See if you can remember what these are in terms of sine and cosine. All right, let's see how that went for you. So tangent, we could call that sine over cosine of theta. Cosecant is 1 over sine of theta. And we've used all of these before when we were doing unit circle kind of stuff. And then secant was 1 over cosine. And cotan, there's two things we could call this. We could call this 1 over tangent, so it's a reciprocal identity. We can also call this, since tangent is sine over cosine, we could call this cosine over sine. So tan and cotan both have this sine-cosine sort of duality going on. Now, all of the reciprocal parts of these identities can actually work in reverse. For example, sine of theta, we could call that 1 over cosecant of theta. We can just flip both sides of any one of these equations up here, any one of these identities. And let's see, cosine, that's going to be 1 over secant. And then we can call tangent 1 over cotan. So it goes back and forth whichever way you need it to go. So these are all reciprocal ratio identities. We're going to look at another group of identities real quick here. So let's say that we have a right triangle on the unit circle. And we already know that the x value is the cosine, the y value is the sine. So that also corresponds with the base and the height of this triangle. Using this triangle, see if you can use the Pythagorean theorem to set up a relationship between sine, cosine, and 1. So our Pythagorean theorem says a squared plus b squared equals hypotenuse c squared. So in this case, that means we have sine squared of theta plus cosine squared of theta equals 1 squared, but 1 squared is just 1. So this is actually the first of three what are called Pythagorean identities. And just a quick note on notation, when we square a trig function, what we're basically doing is, this is like having sine of theta and then multiplying it by another sine of theta. So like sine of theta in the parentheses being squared on the outside. But this is how we write it as kind of a shorthand for that. So it turns out there are two more Pythagorean identities, and we can access both of these by dividing this identity first by sine squared and then by cosine squared. So first I'm going to divide this whole thing by sine squared to generate a new identity that'll be helpful for us. So sine squared divided by sine squared is just going to be 1, anything divided by itself. Cosine squared divided by sine squared, well, cosine over sine we saw up here is cotan. So cosine squared over sine squared is cotan squared of theta. And then 1 over sine squared is like having 1 over sine squared. That's going to be cosecant squared. So we're building on the reciprocal identities that we generated up here. Now let's go through again. So we've got 1 plus cotan squared equals cosecant squared. That's the second of your Pythagorean identities. Let's go through again and this time divide by cosine squared. Sine squared over cosine squared is going to give us tan squared. Cosine squared over cosine squared is just 1. And then 1 over cosine squared is secant squared. So we have tan squared plus 1 equals secant squared for the third of our Pythagorean identities. So your brain is probably ready to explode from all those different identities. Don't worry, we're not going to throw any more of them at you at this point. We do have a few more later, but we'll do some simplifying with the identities that we have in between. So before we try simplifying, let's actually define what we mean by simplified. If an expression, a trig expression, is simplified, that means that we are left with either a constant or a single trig function. And that single trig function could have an exponent on it, like sine squared would be okay. And we also don't want any reciprocals. So 1 over sine of theta, we would turn that into cosecant of theta. So to get something into this condition here, it's not really one size fits all sort of approach where you do a certain bunch of steps and it works every single time. You have to try different things. It's more like a puzzle. However, there are a set of strategies that if you try them in a rough order, they usually get you there more often than not. This set of strategies to help us out, I call APAC, and I just kind of made this up as a way of memorizing a set of things that I'm going to try, and roughly the order I'm going to try them in. So this first A stands for angle identities, and this includes simplifying things that have negative angles inside the trig function, like sine of negative x, and also cofunctions, like for example tangent of pi over 2 minus theta, or cosine of this expression here. So this is always going to be the first thing we like to take care of if we see one of these situations. Now, we haven't really gone over any identities for actually doing this, so we're not going to see any of these until later in the lesson. But when we do, these will come first. The P in APAC stands for Pythagorean identities. So if you see squared trig functions, you're going to want to rearrange and try to substitute for those sorts of expressions using those three identities that we saw on the last slide. Now, maybe you don't see any of these angle things or Pythagorean situations. The second A in APAC stands for algebra. So the things that we can do with regular variables, we can usually do with trig functions that have variables as well. So we can FOIL, which is to say distribute. We can factor. We can cancel, and that includes canceling things that are common factors in a fraction and also that are opposites, like a negative sign plus sign, that could cancel out. We can also, speaking of fractions, combine fractions or split them up, and either might be helpful depending on the situation. So let's say that we've tried all these things and maybe nothing has worked out. The C in APAC stands for cosine and sine. So we know that all 6 trig functions are really just cosine and sine in one form or another. So we could try rewriting everything in terms of sine and cosine. And then once we've got everything in terms of sine and cosine, we might be able to use some of these others again. Probably angles will already have been taken care of, but we might be able to do some Pythagorean or algebra sort of stuff. So these are a good toolkit of things to try out. So with that introduction out of the way, we've, in theory, got everything we need to do the following problems here. So we'll try example 1 first. Pause the video and see if you can simplify this expression. So again, we're looking for a single number or trig function and no reciprocals. All right, so going through my list, APAC, there's no weird angle sort of things going on. There's no squared trig functions. There isn't really any algebra to do. So I come to my last resort there, the C, cosine and sine. I notice that I can turn cotan into cosine over sine. And whenever I do some kind of identity, I'm going to write it in red just so we can kind of keep track what's changing and what's not changing. So now that I've rewritten this in terms of sine and cosine, maybe I can do some algebra and simplify things. The sine up here and the sine down here can actually cancel out. These count as common factors, and we can cross-reduce here. Once I've canceled those, I just have cosine of x, and this is a single trig function, so this qualifies as fully simplified. Next up, we've got example 2, tan of x minus secant of x times kind of the conjugate of that. So pause the video and see what you can do with this one. So just like before, there's no angle stuff to deal with. Pythagoreans, there's no squared trig functions. So I move on to algebra. I can FOIL this whole thing out. I also could turn things into sine and cosine if I wanted, but the reason I save that for last is because that's usually the longest way to get there. If we can handle things before doing that conversion, it tends to be a lot faster. So let's try some algebra here. I can FOIL this out. So I've got tan times tan, that'll be tan squared. We have a tan secant of x and a negative secant tan of x. Those are actually the same term that'll cancel each other out. And then we have negative secant times secant, that's negative secant squared of x. Now that I've got squared trig functions, I'm going to try to use one of those Pythagorean identities because those all have squared trig functions. The one that would help me out here is 1 plus tan squared equals secant squared. That's the original form of the identity. But now in order to use this, well, I can't directly substitute this for anything, for this whole expression here. One thing I could do is I could make my identity look exactly like the expression over here. So if I wanted to get tan squared minus secant squared, well, over here I would have to subtract secant squared and then subtract 1 over to the other side. If I did that, I would see that tan squared minus secant squared equaled negative 1. So we could do that and directly substitute it out and get negative 1 for this expression. Another way you could have done it is you could directly substitute 1 plus tan squared for this secant squared over here. Then you'd have a minus 1 and a minus tan squared when you distributed, and that would again leave you with a negative 1. And lastly, we could move the 1 over here and then swap out tan squared for secant squared minus 1, which again would get us negative 1. So a lot of ways to do it. So pick one and use the identity to get the negative 1 here. Here's another problem to try out. Like the last problem, this one has some things in parentheses, but there is a subtle difference on this one, and you might save a little time if you notice that. Pause the video and give this one a shot. So looking for, again, I don't have any weird angle stuff going on, but my Pythagoreans, I've got not one, but 2 squared trig functions here. So I'm going to try my Pythagorean identities right away. If I FOIL this out first, I'll still eventually get to the answer, but I think you'll find that if you do the Pythagoreans first and try to turn these things that have 2 terms into something with 1 term, things go a lot more smoothly. So what are the identities that would help me out here? Well, for this first one, 1 minus cosine squared of x, I've got the identity sine squared plus cosine squared equals 1. Now, if I subtract cosine squared to the other side and get 1 minus cosine squared, that is going to be the same as sine squared. So I can replace 1 minus cosine squared with sine squared. Now this 1 plus tan squared, this probably looks familiar because we just used it on the last example. We might remember that 1 plus tan squared is secant squared. That's the original identity or something equivalent to it. So I can just replace this parentheses with secant squared. And at this point, I don't really have any algebra to do. There's nothing to multiply together. The only move I have left here is to turn everything into sine and cosine. Secant squared can be rewritten as 1 over cosine squared. So I can write this as sine squared over cosine squared of x. The sine squared is kind of staying where it is, but we're moving this cosine squared underneath it here. And then sine squared over cosine squared, well, that's equivalent to tan squared. So we can call this tan squared of x. So I hope your creative juices are flowing. We've got one more problem to try out in this part of the lesson. So pause the video and give this one a shot. All right, now this one has all 3 co-functions in it, right? Cosine, cosecant, cotangent. So that's kind of cool right off the bat. Unfortunately, there's no Pythagorean or angle identities that are going to help me out right now. But what I can do is multiply these parentheses out, FOIL this out. So distributing the 1, that'll give us cosecant squared plus cotan, or cosecant plus cotan, no squared in there. Distributing the negative cosine, that gives me negative cosine cosecant and negative cosine cotangent. And it's a little bit of a pain, but make sure that you keep writing these variables inside the trig functions, because without the variables, they're not really much of anything. It'd be like having an empty square root function. Anyway, what can we do at this point? Are there any like terms we could combine? It doesn't quite look like it. So these two look similar, but we have a cosecant versus a cotangent to go with the cotan, so that's not going to help us out too much. So what can we do instead? Well, if algebra is not working and there's nothing squared, we go to sine and cosine, right? That's always kind of the fallback. So cosecant, I can convert that to 1 over sine. Cotan is cosine over sine. And then cosine times cosecant, well, cosecant is really 1 over sine, so I can rewrite this as cosine over sine. And then this last one, I'm going to have cosine times cosine over sine. So this looks even worse than what we started with, but there is something kind of neat here. If you look at these two terms in the middle, and we couldn't see this before because things were in different forms, but what do we have here? We have a positive cosine over sine and a negative cosine over sine. So those are actually going to cancel out. And what is left? Well, the things that are left, you'll notice that we have sine in the denominator of both of those fractions. So we could move these two terms into a single fraction. If we did that, I mean this over here is cosine squared, we would have 1 minus cosine squared, all of that over just one of those sine x sort of denominators. So it's been a little bit of a journey. Where do we go from here? Well, we always, after we use one of these moves, it's always good to go back to the beginning of APAC and see if there's anything else to do. So Pythagoreans, we now have a squared trig function. Let's try some of that out. We know that sine squared plus cosine squared equals 1. And again, if we do 1 minus cosine squared, that gives us sine squared. So I can replace this numerator with sine squared. And this is really just sine times sine, so I can cancel out one of the sines up there with the sine of x in the denominator. So when the dust settles, that leaves me with just sine of x. So this concludes part 1 of our lesson on using trigonometric identities. Pause the video, try out some of those practice problems, and in part 2 we'll learn some more tricks and also some new identities. See you then. Welcome back for part 2 of our lesson on using trigonometric identities. In the next couple of examples, we're going to be able to use a little bit of factoring to help us out. So with that little bit of a hint in mind, pause the video and see if you can use that to help simplify this expression. All right, so going through our list of things, there's no weird angle things going on here. Pythagoreans, we do actually have a squared trig function here. So it would be possible to use one of our identities, and that would actually get us to the answer probably in about the same amount of time as the thing that I'm going to show you here. But the other thing we can try here is a little bit of algebra. We've got two terms, and each of them has a common factor of cotan in them. This first one's got 3 of those cotans, but we have one over here as well. So one thing you can do is factor out a common trig function from expressions. So we can take a cotan of x out of both of those. That'll leave us with cotan squared of x minus, this will be cosecant squared of x. And at this point with these, we've got not one but 2 squared trig functions. So if we weren't thinking Pythagorean identities before, now is a good time to start thinking that. So we've got the identity, which we haven't used in this particular lesson yet, of 1 plus cotan squared equals cosecant squared. This is the one we got by dividing sine squared plus cosine squared equals 1 by sine squared. Anyway, how can we use this to simplify this expression? Well, if I subtracted cosecant squared to this side and moved 1 over to the other side, I would have cotan squared minus cosecant squared equals negative 1. So I can just replace this whole thing in here then with negative 1. And again, that's not the only way to do it. You could just replace this cosecant squared with 1 plus tan squared, cotan squared, and you'll get here eventually as well. But at this point, there's nothing else to do except multiply this. So this comes out to negative cotan of x. Here's another example where factoring might be helpful. and Pythagoreans as well. This one is a little bit trickier. I'll just give you a quick hint and then set you loose here. Sometimes you have to do something that appears to look like unsimplifying before you can actually simplify. So with that in mind, pause the video and see where you can go on this one. All right, so we have a squared trig function, so Pythagorean identities might be of use here. We've got that sine squared plus cosine squared equals 1 identity. Now, if I subtract cosine squared, we've done this a few times, right? We know that sine squared and 1 minus cosine squared are the same. So I could, if I wanted to, replace this sine squared of x with 1 minus cosine squared of x. Now, this would be the first time we've actually done a substitution in this direction. Usually we take two things and turn them into one thing. So why would it make sense to go the other direction? Well, these two things here are actually a difference of perfect squares. You can factor this using your a plus b, a minus b shortcut. You could split this up into 1 plus cosine of x times 1 minus cosine of x. And that would normally not be helpful at all, except that we have a 1 minus cosine of x in the denominator, so it's helpful now. So those actually will cancel, and we just have 1 plus cosine of x minus this little stray 1 out here. The 1 and the negative 1 cancel, so we just end up with cosine of x. For this next example, there's something a little bit weird going on. I actually kind of highlighted it in blue in the example here. We have this negative x inside one of our trig functions. And this is our first time encountering this situation. Whenever we have a negative angle, we're going to need to use one of what are called the negative angle identities. So here are the identities that will help us out here. And by the way, we're not going to rigorously prove these, but they are based on the idea of even versus odd functions. So we'll just go through them one at a time, and I'll kind of explain where this is coming from. But here we go. So let's say that we have cosine of negative x. Now, cosine is an even function. We know in general, and we know this because cosine has y-axis symmetry if you look at the graph. So even functions have the property that f of negative x equals f of x. So cosine of negative x then just equals cosine of x. And if you still don't really believe me, you can just test this out with an angle. Like let's say we do cosine of negative 60 versus cosine of 60. Well, cosine of negative 60 is 1/2. It's in quadrant 4, but it's an even value. Cosine of positive 60 is also 1/2. So that's a quick little example of how that works. Now let's talk about sine and tangent. Sine of negative x, sine and tangent actually, those are both odd functions. If you look at their graphs, they have rotational origin symmetry. So that gives us the rule, in general, we have f of negative x equals negative f of x. So specifically in this case, this means that sine of negative x equals negative sine of x. And again, try out an angle if you don't believe me. Sine of negative 30 would be negative 1/2. Negative sine of positive 30 would also be negative 1/2. So this one works. And then finally, tan of negative x equals negative tan of x. Same reason as the sine rule here, because tan is an odd function. And you can try out negative and positive 45 degrees if you don't believe me on that one. So, with all that said, we're going to use one of these identities to help us out down here. And just like we mentioned before when we were going over APAC, if there's something weird going on with the angle, like a negative angle, typically you're going to want to make sure you take care of that in the first step. You might do other things alongside it, but you're going to want to handle that as soon as possible. So with that in mind, pause the video and tackle this example. All right, so we've actually got three things that I'm going to do to start us off here. The numerator has Pythagorean identity kind of set up in it. We have the identity 1 plus cotan squared equals cosecant squared. So I'm going to use that to simplify my numerator. If I subtract cotan squared from both sides, I see that cosecant squared minus cotan squared is really just 1. So that whole numerator I can just turn into 1, which is awfully nice. Now let's take a look at these other things in the denominator. Sine of negative x we know because sine is an odd function, is going to be negative sine of x. So we'll do that little conversion, and it doesn't look that different, but the key here is that you have a positive x angle in there, which means that this sine of x can interact with a bunch of things that this negative x was preventing us from dealing with. Now cotan, we can actually also rewrite that while we're at it. We can rewrite that as cosine over sine. So I could have done this in 3 separate steps, but I just kind of combined all 3 into one step because it was convenient to do so. Now taking a look at what's left after I've done all of that, this sign and this sign down here can cancel out. So this is 1 over negative cosine of x. And then we don't like reciprocals, so I'm going to turn this into negative secant of x to get my final answer. For this final example on this part of the lesson, we have some weirdness going on here. We have tan of pi over 2 minus theta times sine of theta. So what is going on with this weird angle? So we're going to back up a little bit and revisit some of our trig functions that you've been using this whole time, maybe without knowing what they really mean. So I'm talking specifically about cosine, cosecant, cotangent. None of which are in this problem, but I'll get to my point in a sec here. What do you think the co in all those functions stands for? It actually stands for complementary. So here's the deal. A trig function's value at an angle, it turns out, is the same as its cofunction's value at the complementary angle. Now this probably doesn't make a whole lot of sense the way I've written it, so here's a concrete example here. Sine of 30, which is 1/2, is the same as cosine of 60. That's also 1/2. The point I'm trying to make here is 30 and 60, those are complementary. Those add up to 90, don't they? So that's what this cofunction actually means. If you take the cofunction of the complementary angle, you get the original function at angle. So that allows us to actually set up a whole bunch of identities with these cofunctions. So these are our cofunction identities. So the first one, as we kind of saw right here, the sine of an angle is the same as the cosine of the complementary angle, which we're going to express as pi over 2, that's really 90 degrees, minus theta. And we've got relationships for all the 6 trig functions like this. So secant, that's the same as cosecant of pi over 2 minus theta. Tangent is the same as cotangent of pi over 2 minus theta. And all of these relationships work in reverse. So cosine is the same as sine of the complement. Cosecant is the same as secant of the complementary angle. And cotan is the same as tangent of the complement. So this is 6 new identities, although it's kind of just 3 and 3 that are reversals rolled together. These will help us out on problems where we see this sort of thing. Now, it's kind of annoying to have 6 new identities to deal with. The good news is these are super easy to spot. You know you don't really need to use these unless you see this weird kind of angle business going on. So with that in mind, pause the video and see if you can use these to help you simplify this last example. All right, so in our APAC setup, angle identities comes first. So let's take care of this tan of pi over 2 minus theta. We see that that's really going to be the same as cotan of theta. This is the tan of the complement, so that's really the cotan. And that's going to help us out because we know that cotan, we've seen this a few times, is cosine over sine. So this sine and this sine can cancel, and that means our final answer is just cosine. So congratulations on making it this far. If you're doing the CP version of the course, this is actually the end of the lesson. You can power this thing down and go try out some more problems involving these weird angle identity problems and call it a day. If you're doing the honors, this is the end of part 2, so you also get a break, but you're going to be coming back to do one more topic when we return on verifying identities. See you then. Welcome back if you're rejoining us for the honors portion of the lesson. In this one, we will be verifying some trigonometric identities. So the idea here is that they're giving us an identity, and we just need to show that the 2 sides of this equation are equivalent. That's ultimately our goal. We want to end up with something equals something else and having the same thing on both sides. Now there's a little bit of a catch. We are not allowed to use any properties of equality to do this. Even though there's an equals here, it's not a real equals. This is kind of like an equals question mark that we're trying to prove. So since we can't use any of the properties of equality, because again we haven't proved equality yet, that means we can't do things like add something to both sides or divide both sides of the equation by cotan or anything else like that. So what does that leave us with? Our general strategy on these, since we can't treat them like an equation, is we are just going to simplify one side of the equation until it looks like the other side. And you actually could do one side or the other side, or you could actually simplify both sides at the same time. Typically, it's going to be a lot more efficient and easier if you just pick one side to work on and stick with that one side. And if you're wondering which side to work on, it's usually easier to simplify than unsimplify something. So I would pick the side that looks less simple and keep at it until it looks like the side that's more simple. So with that in mind, pause the video and see if you can get one of these sides to look like the other side by working only with one side. Alright, so for this problem, the left side looks a lot less simple, so I'm going to start with the left side and see if I can turn that into cosine. So I'm going to deal exclusively with the left side. I'm going to say that this left side equals stuff. The stuff that it equals is being generated from this left side alone. It has nothing to do with this cosine over here, even though that's our eventual goal. So one thing I notice on the left side that I can do right away in my APAC setup here is I have this angle, this cofunction going on, so I can turn cosine of the complement into sine of x. So I've got sine of x that this thing equals, and I've still got this cotan here as well that I can work on. This cotan can turn into cosine over sine. So now I can just cancel out these sines here, and that leaves me with just cosine of x. Since cosine of x is the thing that I had on the right side to begin with, I have proven this identity, and I'm actually done with the problem. So now the good news on these problems is, you know what the answer needs to look like. You know you're supposed to get the same thing on both sides, so you'll know when you're done. It's just a matter of how you get there. Here's another identity for us to try out. This one's got a negative angle in it, just to practice that skill. Pause the video and give this one a shot. Alright, so just like before, I'm going to pick the less simple side, which is the left side here, and just work on that. First thing I want to do is take care of this negative angle. So I know that sine of negative x is negative sine of x. So what I can rewrite this whole thing as then is negative sine of x, that whole thing squared. And then tan squared, I can also change that a little bit while I'm at it. I can make that sine squared over cosine squared down there. So that looks awfully ugly, complex fraction, but we're going to quickly take care of that. So two more things I'm going to do for my next step. One of them is cleaning up this squared thing here. If I'm doing a negative times a negative, that's actually a positive. So this negative sine of x squared is actually just positive sine squared of x, which is kind of nice. Also, I'm going to multiply by the reciprocal of this fraction down here. So I'm multiplying this by cosine squared over sine squared. And I see once I do that, that these sine squareds can actually cancel out. So that just leaves me with cosine squared for a final answer. And that's a final answer because it's what was over here on the right side. Here's our next example. Pause the video and try this one out. Alright, so let me work on the left side here. It looks a lot less simple than the right side. So there's a couple ways I could go on this. I see that I've got a squared trig function, so I actually could use 1 plus tan squared equals secant squared. And I guess I could replace this with 1 plus tan squared, and then that would cancel out with the 1 here and give me just tan squared over secant squared. So that's totally one way to do this problem, and it'll get us there. But what I chose to do instead is I split this fraction up into secant squared over secant squared. minus 1 over secant squared. So I just split up the fraction with the same denominator. Now the reason that this was helpful for me is because secant squared over itself is just 1, and 1 over secant squared is going to be just cosine squared, so 1 minus cosine squared. And we know, we've seen many times from our sine squared plus cosine squared equals 1 identity that 1 minus cosine squared is just sine squared, which is what I was trying to get on this right side. So that's another way of getting this problem to prove the way it needs to be. Here is our final problem, and we saved the best for last. This one is definitely tricky. Pause the video and see what you can do with this. Okay, so if you weren't able to actually solve this one, don't worry about it. There's a technique that we haven't really seen before in this lesson that we're going to introduce here, but let's see how far we can get short of using that technique. So choosing which side I want to simplify, this is a tough one because, I mean, the right side, we've got everything in terms of cosine and sine and no way to really do anything else over there. On the left side, really all we can do is turn this into cosine and sine. So I can make this 1 over cosine plus sine over cosine. Now that does have an advantage. Since I've got the same denominator, I could merge this into a single fraction, 1 plus sine of x over cosine of x. And a number of you probably got here, and then you're like, well, it kind of looks like the thing on the right side, but it's still kind of different. So how do we go from here? So one little trick you can use when you have a 1 plus or a 1 minus a trig function is you can multiply by what I like to call a trig conjugate to set up a Pythagorean sort of situation. So what I'm going to do here is I'm going to multiply by 1 minus sine of x. If I do that, that'll give me 1 minus sine squared of x, which we can work with. We've used that a few times. But we can't just multiply the numerator by 1 minus sine of x. We have to multiply the denominator by 1 minus sine of x as well. So this will allow us to move forward in the problem. If you would like, feel free to pause the video and see if you can take it the rest of the way. Otherwise, just follow along. So multiplying out the numerator, as we said, this is going to be 1 minus sine squared of x. The denominator, there isn't really a whole lot we can do. I can just do cosine times 1 minus sine of x. I could distribute this cosine, but I'm not really sure there's a value in doing so. What I can do, though, is work a little bit more on my numerator. We have the identity sine squared plus cosine squared equals 1. So we could, if we subtract sine squared from both sides, we see that is the same as cosine squared. Well, one of the cosines up here and this cosine down here can cancel out. So that's going to leave us cosine of x over 1 minus sine of x. And that, it turns out, is exactly what we were trying to get in the beginning. So a little tricky, but this is a new little trick you can use to get your way on these problems. So this concludes our marathon lesson on using trigonometric identities. It's a lot, but on the bright side, I mean, this is what the Greeks had to do 2,000 years ago anytime they wanted to prove their identities. For us, these days, we just have to show our driver's licenses. Till next time, Mr. Sutton signing off.